Good morning, everyone. Today I'm going to present about the equation of state for non-ideal gases. I will be presenting about the critical temperature and pressure and the viral equation of state. For the critical temperature and pressure, the highest temperature at which a species can coexist in two phases, liquid and vapor, are called as critical temperature of the species. And the corresponding temperature is the critical pressure PC. Substances at Tcn PC is at a critical state. I present first. Sorry. At 25 degrees C, water will condense at a very low pressure and the density of liquid is more than 4 orders of magnitude than of the vapor. The higher temperature, the condensation pressure increase and the density of vapor and liquid at condensation approach each other. At 37.415 degrees C, the density at two phases are equal, and above that temperature no phase pressure is observed, no matter how high the pressure is raised. The term gas and vapor are often used interchangeably. A vapor is a gaseous species below its critical temperature. A gas is a species above the critical temperature at a pressure low enough for the species to be more like a vapor than a liquid. Substances at temperature above Tc and pressure above Pc are called as supercritical fluid. So here is the table below shows the temperature, critical temperature and the pressure condition, pressure density at at vapor and density at liquid phase. The first question is, the critical temperature and pressure of isopropanol are 508.8 K and PC at 53.0 atm. Isopropanol is in gaseous state at 400 K and P at 1 atm. Would it be classified as a vapor or a gas? So if you refer back, if the temperature is below, then the critical temperature is called as vapor. So the answer here is vapor. Next question, isopropanol is compressed isothermally at 400 K until at pressure PA a liquid phase forms. The vapor and liquid densities at that point are respectively density of vapor A and density of liquid A. In a second experiment, isopropanol is compressed at 450 K until condensation occurs, at which point the pressure and vapor and liquid densities are pressure at V, density of vapor V, and density of liquid V. What are the relationship between PA and PV? Density at vapor state and density of vapor state V and density of liquid state and density of liquid state in at V. So if you refer here, PA is, the difference between the first and second experiment. PA has the smallest, smaller pressure than V. For V, you have no idea because we don't know the answer. For C will be more than density at liquid phase at A is higher than B. Second question, the third question, if isopropyl at 550 K and 1 atm is compressed isothermally 200 atm, will it will consider form? What term might you use to refer to the fluid at its initial condition, at its final condition? So the answer is gas and supercritical fluid. Because the critical temperature from the initial one is higher than the initial one, and the pressure also is higher than the initial one. That's why it's called supercritical fluid. The next one, we'll talk about the variable equation of state. A variable equation of state expresses the quantity of PV over RT as a power series in the inverse of a specific volume. So for this equation, need to memorize, yeah. Sorry. And this table also given because you need to calculate you need to estimate the B. Yeah, the eccentric factor. For example, 2 gram of 2 gram mole of nitrogen is placed in a 3-liter tank at 150.8 degrees Celsius. Estimate the tank pressure using the ideal gas equation of state, and then using the bar equation of state, truncated up to the second term, taking the second estimate to be correct. Calculate the percentage error results from the use of the ideal gas equation at the system condition. So first of all, you need to change temperature to Kelvin because it is the SI unit. So 150.8 73 point, you will get, oh sorry, it's negative, yeah. uh, you will get 122.4. Yeah. And you need to calculate the V as well, which is 3 liter over 2 gram. You will get 1.50 liter per mole. a little bit more. And using the for equation, you must use this equation to calculate to find V in initial and final. Sorry, before we use the for equation, we must find the P idea first. Using the P over PV over NRT now. R is the gas constant, yeah. You calculate, oh, then you get 6.73 ATM. The next step is you need to use the for equation to calculate V coefficient. Semua paham kah? Hello?
Paham, Sam.
Paham.
Okay. Since this is nitrogen, TC and PC is not given in table. You need to find it by yourself. So TC is 126.2 K. PC, then you get 33.5. And from the pizza exchange factor, it is given as 0.040. Is here, yeah? Nitrogen. The first step is you need to find the value of reduced temperature, which is Tr equal to temperature over Tc. T is given that you calculate just now is 122.4 K of the nitrogen is now here. And Tc will be 126.2 K. And you will get 0.970. Using the equation 5.3 now you need to calculate this. And this one is already given, so you can calculate already to find the V initial. And you will get negative 0.36. For the V final, you also calculate using the same one as the 5.34 but different TR, yeah? Same TR but different notation. And you will get negative 0.056. Lastly, you need to calculate V as well, but the eccentric factor is given, which is 0.00. Sorry. And you get negative 0.113 liter per mole. After that, you need to use the 5.32 back, calculate the pressure. I mean, express in terms of P, if referred earlier. I mean, rearrange this equation, then you get this. Substitute all the values. And you get 6.19 atm for pressure. Because the question asks you to calculate the percentage error. We all know that P ideal is 6.73 atm. and P is 6.19 atm. Calculate using the percentage error. And you will get 8.7% error. That's all from my last part. Thank you. Now I will handle the next one to Armin Zakrin for cubic error equation.
Okay, thank you, Sam. Can you guys see it? Boleh nampak?
Cannot.
Cannot.
How about now? Sekarang boleh nampak?
Boleh, boleh, boleh.
Okay. Okay, for my next part, before this about from Samuel. Now for my part is about cubic equation of state here. For this cubic equation state, which are often also called the semi-empirical equation of state, are using the repulsive term proposed by van der Waals. These various attractive terms have been proposed in the literature, some of them present. And this equation is one of them by using this cubic equation of state. Here is the pressure equal to the gas constant times with the temperature over with the V minus B and minus with A over with V square. Where this is the this is the parameters for the equation for A and B. Here A is 27 R square times with T square Tc. Here Tc is the critical temperature and over with 64 Pc. Here is the pressure critical. And number 4b is R times with the temperature critical over with 8 times with pressure critical. This cubic equation state including the Redlich-Kwong, Swift, Redlich-Kwong, and Peng-Robinson equation. So you guys know what is the Peng-Robinson equation, right? Before it we learn from the programming. And here we will use the SRK expression to illustrate the general characteristic of cubic equation to of state. This is the SRK equation state for only only is different from this. This one is a over b square, but this one is rt over v minus b equal minus alpha a over with v times with v plus b. And here is the parameters for the equation, and you guys know this is for the a. For finding the value of a, we can sub in here. For b, we can also sub in here to find the answer for the pressure. And m also we can use it, but this m here, the eccentric pressure, the eccentric factor, like Samuel discussed before this from the table, from the table, some of from the equation, from the question. And for the alpha is here 1 plus m 1 minus square root of tr bracket square here. So here tr is tr equal to t over tc. So here we can find the tc from the table, and the temperature, normal temperature, is already be given from the question. So it's much easier based on the question what they need. So you guys understand? So korang faham?
Paham.
Okay, that's all for my parts for about cubic equation of state. So thank you. So I will lend for the next part to Rosna or Sonia.
It's me. Nampak kah?
Okay. Boleh.
Boleh, Son.
Okay. Okay, for compressibility factor of ideal gas, as we know, the ideal gas law can be defined by PV M equals to RT, where PV is the pressure, Vm is the molar volume, R equals to universal gas constant, and is the temperature. And from the ideal gas law, it is modified to calculate the compressibility factor, which is Z equals to PVM equals to RT. And Z value can also be expressed as Z equals to the actual volume over the ideal volume. As we already know, the Z value of an ideal gas equals to 1. And for real gas, the Z value may be positive or negative, depends on the intermolecular forces of the gas. Like when Z is more than 1, the actual volumes will be greater than the ideal value, and when Z is less than 1, the actual volumes will be less than the ideal value. As the real gas becomes closer to the critical point or its saturation point, the larger the difference from ideal gases behavior. I think that is all from me. Thank you. You guys paham kah?
Paham.
Clear.
Yeah. Thank you.
Boleh nampak kah?
Boleh?
Ya, boleh nampak.
Boleh?
The compressibility factor of each gases is not the same. So the compressibility factor of the gases can be measured separately using using van der Waals equation and Sauve-Rayleigh-Kwong equation. And then the Z value can be estimated using the generalized compressibility chart. The method is very simple. The first step is look up at the critical value, the temperature critical and pressure critical of the species from physical property table B1. And then next, calculate the reduced temperature and reduced pressure, which is TR equal to temperature over critical temperature, and the pressure reduced is pressure over pressure critical. And then lastly, look at the Z value on the generalized compressibility chart, which plots Z versus pressure reduced for the specified value of TR. So this is the the generalized chart. This one is for reduced temperature for the Z factor at low pressure. This one at medium pressure. And lastly, this one is for high pressure. Okay, that's all from me.
Ada sesiapa yang nak tanya soalan? Sebelum kita end our meeting session. Ada?
Ada soalan tak? Yang lain ada soalan tak?
Saya tak.
Tak ada.
Okay.
Tak ada.
Okay. For our meeting session now is end. Thank you so much for present your parts in chapter 5.3 and 5.4. So you can leave this meeting. Thank you.
Bye.
Bye.
Bye korang.
You guys, bye.